And let's then probably move to the next speaker, to Yulia Ageeva. Yulia is going to tell us about genesis and bounds in Horndeski series, strong gravity in the past. Okay. Go ahead, start.
Can everyone hear me?
Yes.
Okay, hello to everyone. First of all, I would like to thank the organizers for the possibility to give a talk here. Yes, today I'm going to talk about genesis and bounds cosmologies in the framework of Horndeski theories with strong gravity in the past. My talk is based on two works in collaboration with Valery Anatolyevich Rubakov and Pavel Petrov. So let me start with a very, very short motivation, since today during morning session, the motivation to study alternatives to inflation was already discussed. So we want to study genesis and bounds to somehow complete inflation, to provide early time completion to inflation. And all we know that genesis and bounds are initial singularity-free models, and we can build such non-singular cosmologies in the framework of Horndeski theory. So we are interested in such Lagrangians. Next, we want to build stable genesis and bounds, of course, during whole evolution of the universe. And it means that we should avoid many no-go theorems. And the last interesting point, also connected with avoidance of no-go theorems, is strong coupling regime. We talk about it later. And to avoid this possibility, we should choose right parameters of the Lagrangian. So let's talk shortly about all these points. Let me briefly remind you the full Horndeski Lagrangian, but actually for us it is enough to study only a subclass of this theory without G5 term. Okay. And to talk about stability of our model, let me remind you the second order action for perturbations in our model. We want to study IDM metric with Laplace function n. N eta is shift vector. Gamma Eg contains scalar perturbation zeta and tensor perturbation h, and for them we have second order actions, since alpha beta are non-physical variables, and we can obtain constraint equations, solve them, substitute them back to action, and arrive to these two expressions. Here, to study stability of our models, we need to know something about these coefficients. And especially we want to obtain right asymptotic for them in order to avoid no-go theorem, especially in full Horndeski theory. This no-go theorem was given by Tsutomu Kobayashi. And the only possibility to avoid no-go and obtain stable cosmology during whole evolution is to fix or set tensor coefficient from second order action runs to 0 in the past. But let me remind that this coefficient is nothing but G4 function, and in Lagrangian it stands near Ricci scalar. It means that this is nothing but effective Planck mass, and if we have this asymptotic, it means that effective Planck mass goes to 0 in the past, and this is our naive signal of strong coupling regime in the past. But this is only the second order action, and to understand the truth and if they're really a strong coupling problem or not, we should go further and consider higher order action. Here I should say that for us it is easier to work not with covariant formalism of Lagrangian, but with ADM formalism of Lagrangian. And there is one-to-one correspondence between this function. I drop all details about it, just we want to work with this formalism. For us, it is simpler. Okay, the idea is that we want to expand this action in all perturbations of our metric, and we want to find a good form of this Lagrangian function in order to obtain stable, non-singular, demanded bounds or genesis model without strong coupling in the past. Again, it is convenient to divide these Lagrangian functions in two parts connected with time. Function f is a function of time, and another functions of lapse. And here we have some constant parameters mu and delta. Okay, and in order to obtain avoidance of no-go, we set this function has the following asymptotics in the past. Also, we want to study genesis and bounds. Here I talk about genesis for now. Further, I also show that the same we can obtain for bounds model. Also can avoid strong coupling regime in bounds too. For genesis, we have the following background solution. Scalar factor runs to 1. At the same time, the same we have for background lapse function. And Hubble is given by this asymptotic in the past. Okay, it means that in the past we have empty universe, flat space, time, and when time runs to 0 from minus infinity, Hubble grows. The main feature of this model is that we can avoid no-go, since we have good asymptotics of all these functions in Lagrangian. And as I told previously, we face with strong coupling. So let me remind you our metric. Here we have again, let me repeat, alpha, beta, and even one more and eta transverse vector perturbation. These guys are non-physical, and we can find constraints equation for them and obtain finally action, higher order action only for zeta and Ageeva perturbations. So we're interested in these two physical perturbations, zeta and Ageeva. Also, we set residual gauge freedom for these two values. Okay. What we want to do is that is to substitute this metric into our Lagrangian. Since we have asymptotic in the past, concrete asymptotic in the past for all these functions, we can schematically rewrite our integrand of action as follows. And very, very important that we have overall prefactor here with parameter mu. It really simplifies our lives in our calculation of higher order analysis of strong coupling, since parameter mu our constraints for alpha, beta, and eta transverse are independent on this parameter and depend only on some numbers, combinations of delta, and some numbers. Okay, let me, due to the lack of time, drop important details about constraint equations for alpha, beta, and eta transverse. and directly go to schematic form of integrand of the action, or schematic form of each term in higher order action. Here, PQ index means that we consider a term with P number of scalars equals P and Q tensors. Also, it is important to note that for each term we have time behavior with DL. This is a combination of delta parameter and some numbers. And for each term, we have some number of derivatives, CL. CL is a sum of time and spatial derivatives. Okay, in order to, if we want to talk about a strong coupling problem, of course, we should canonically normalize our fields H and zeta. So we proceed with it here and substitute them back to the action. We can obtain some final coefficient for each term in Lagrangian lambda L, capital lambda L. And find its dimension. Okay, it depends on number of scalars, number of tensors in this term, for this term, and the number of derivative, of course. Potentially, only terms with the following inequality potentially lead to strong coupling only, so we are interested only in such situation. And after some calculation, we also can find important feature, characteristic strong coupling energy scale. The next step is to compare this scale with classical energy scale, which we can obtain from Hubble parameter and its time derivative. Sorry. Again, after some calculations, we arrive to constraints on two parameters in our model, mu and delta, parameters of the Lagrangian. And one can understand, one can see that the strongest condition comes from terms with the biggest difference between time behavior index DL and difference between DL and number of derivatives CL. So our main goal is to find the largest difference among all terms in higher order Lagrangian. Now you can ask, is it even possible to somehow calculate higher order Lagrangian, do such a terrifying calculation? Of course, in general, the answer is no, but we apply some considerable simplifications, and with them, it is possible to naively analyze through dimensional analysis the strong coupling problem in all higher order, in higher orders of action. Okay, let me briefly list our simplifications. First of all, we neglect all numerical factors in action, and we don't care about tensor structure. It means that we neglect all possible constellations. In other words, we just consider all possible terms. Okay. The second idea is that we keep only those monomials in action or in integrand of action which have the largest value of this difference, as I previously told. For us, it is convenient to employ new notation, new index between each term in constraint and in unconstrained action connected with this difference, since we want to obtain terms with the largest one. And since this moment, we do not distinguish monomials with different time behavior index D and the number of derivatives. We want to study only this difference. So this is very important simplification in our model. The same idea we apply in original action with alpha, beta, and eta transverse, zeta and H, since here I talk about unconstrained action already, but of course the first step, we should study original action with all perturbations and at the same time constraint equation. And everywhere we again in higher order action we consider try to keep only terms with the largest difference between time behavior index and the number of derivatives. Okay. Another maybe strange but also considerable simplification is that we replace some terms in original higher order action with new ones with larger difference between D and C. For example, we replace, for example, this expansion with this one. I should remind you that delta is bigger than 0. So really this index, meaning D minus C, larger than this one. And this simplification also helps us to proceed with calculations. The last simplification also connected with addition of arbitrary terms to higher order Lagrangian. I should say that in Lagrangian, in ADM Lagrangian, we have A2, A3, A4, and B4 functions. And each of them, but not B4, have this expansion 1 plus alpha square. So we just want to make them the same in this manner. That's why we add alpha square plus blah, blah, blah to this term as well. Okay, again, without any details, due to the lack of time, unfortunately, I want just provide the result that from higher order integrand of the action, we obtain the following D minus C index for unconstrained Lagrangian higher order. And from second order action, it's important to divide them. Distinguish them. We obtain the same new notation, new index D minus C. And finally, we arrive to the interesting result that the strongest constraint on mu and delta comes from situation with 3 scalars and no tensors. And we have already studied this situation in explicit manner. We have studied cubic order of scalars with exact coefficient here with 17 different terms in action and obtain 17 different constraints, and the strongest one exactly the same as we obtained here from higher order analysis. So it's really interesting result, I guess. Okay, what we can do after that, we want to, for example, build a specific concrete model of genesis and bounds, since we indeed can avoid strong coupling problem, build something stable during whole evolution, and in the framework of Horndeski theory, we can build bounds and genesis. Okay, since we talked about genesis previously, let me show you concrete numerical example of genesis model. We just choose mu and delta, which satisfy our condition of no strong coupling, condition of no-go theorem, avoidance of no-go theorem, And also we want to obtain stable cosmologies, and so there are other ones conditions on all parameters. For example, we choose A2 small and A3 small in such a way in order to avoid instabilities. Okay, let me show you our numerical example. For example, Hubble parameter has the following form. As we want everything starts from empty universe, from flat space-time, and then smoothly transit to inflation epoch. Also, we can prove the stability of our model. Here I show only scalar coefficients and scalar speed of perturbations. And for tensors, pictures not so funny and interesting. They are just constant and equal 1. Okay, after healthy genesis, we decided to build healthy bounce model. It is also possible in the framework of our setting. And further, we decided to sew our bounce with inflation and even with reheating or kination stages. So we want to proceed with contraction, then go to bounce moment, then to inflation and kination epoch. It's interesting that kination is driven by conventional GR. So it is important to again find the right form of the Lagrangian to obtain kination epoch. For that, we modify our Lagrangian functions in the following manner. For genesis, you remember that we have delta parameter, but bounce can be built without this parameter. It's great. And also, since there is no delta equals 0 in this model, the strong coupling analysis can be done totally in the same way. And final result is just then delta equals 0 for constraints on mu. So mu must be smaller than 1. This is the no strong coupling condition for bounce model. So it's also very beautiful and simple result here. Okay, but another feature which we apply to Lagrangian function to build healthy bounds is that we add some functions of time into this small A2 and A3. We did this strange movement in order to obtain healthy and stable transition between contraction bounce to inflation epoch and from inflation to kination stage. Since it is impossible to do these transitions with some constants here, unfortunately. So this is just some game or some trials and errors way. Okay, for bounce model, we have the following solution. During evolution of the Hubble parameter, it changes its sign. This is the bounce moment. Everything starts from contraction, then bounce, then Hubble begins to grow with a positive sign. Okay. Also, I should say that we again always demand during whole evolution the positivity of these coefficients from second order action. And I guess I forget to say that we always demand that the square, the speed of perturbations, both tensors and scalars, must be smaller than speed of light, of course. I guess this is the most interesting models. Okay, again, another condition for healthy bounce model is that we should get around no-go theorem. We also want to avoid no strong coupling regime, and for contracting scenarios, we also can face with Belinsky-Khalatnikov-Lifshitz phenomenon, and this problem provides us with another constraints on model parameters. So all these points, I list these points just in order to show you the reasons for constraints on model parameters in bounce model. We want something non-singular, we want to obtain bounce, we want everything be stable, we want to avoid strong coupling regime, and we want to avoid Belinsky-Khalatnikov-Lifshitz problem. So all these constraints gives us the reason to find the right form of function in Lagrangian. X, v, y, and ft functions must have some interesting and right form. Okay, for example, at early times, when time runs to minus infinity, all these functions in Lagrangian are some constants. And we draw a beautiful picture of space of parameters x0 and y0 determining their early time asymptotics. So if you take parameters from this white, I don't know, kind of triangle with v0 bigger than 0, you can obtain a healthy beginning of your cosmology contraction and bounce. Okay, next stage is inflation after bounce. Here we want to have again constant values of function x, v, and y, since this provides us constant value of Hubble parameter, and constant value of Hubble parameter, of course, this is the inflation epoch. Again, here the conditions for these parameters coming from the stability of our stage during whole evolution. Finally, we go to the kination epoch. Here we again find the right appropriate form of x, v, and y function in order to obtain this solution for scale factor and and Hubble parameter. Sorry, I guess there is no more time for me, but actually this is the final slides. Okay, the solution for bounce model is given here. We start from contraction, then go to bounce moment, then Hubble grows, and we smoothly transit to inflation. Again, we prove the stability of our model for scalars and for tensors. Ft equals to gt, I should say, and the scalar speed of perturbation, scalar perturbation, smaller than 1. And this is the following stage: inflation after bounce and smooth transition to kination epoch. Okay, I also want to show you the key point how we obtain smooth and healthy transition between these, for example, between inflation and kination. We find by trials and errors good form of x, v, and y functions. For example, here I show you the function x. This interesting I don't know how to say, interesting part of x function helps us to obtain transition to kination, for example. Again, I prove the stability of this moment, this period, this transition from inflation to kination. And the final model we have built is interesting and non-standard contracting genesis followed by bounds. Here we again find some form of our functions in Lagrangian A2, A3 small letters, and to obtain this model, contracting genesis and bounds, we also turn on time dependence in B4 and A4 Lagrangian function. So in this model, we start from flat space-time, then slowly contract, then Hubble has bounds, and then Hubble grows, and somehow in a strange manner goes to inflation stage. Again, we prove the stability of our model and speed of perturbation smaller than 1. Okay, what we have done, we have studied non-singular cosmologies like genesis, bounds, and even one new modified genesis plus bounds scenarios in the framework of Horndeski theorem. In subclass of Horndeski theory, which is even simpler than full Horndeski Lagrangian. We can avoid any instabilities during whole evolution. We can sew our bounds and genesis with inflation, and then even with kination. Also, the interesting point here that we have studied strong coupling problem in all higher order of action by using naive dimensional analysis. And we have built several healthy, concrete numerical models of these cosmologies. Okay, the next interesting question here is it possible to obtain power spectrum which will be in agreement with observational data in our models? Okay, thank you for your attention.
Thanks a lot for this detailed talk. And I see, I don't know who was the first, but let's ask Alexey Alexandrovich to go ahead with his question first.
Okay, thank you, Yulia, for this very interesting talk. I have two questions, mathematical and physical, both regarding to the general idea of genesis. First, from a mathematical point of view, what is the structure of your point at t equal infinity from the point of view of the theory of differential equations? Is it a saddle point or okay? And then from the physical point of view, just because you have unstable Minkowski, why we don't see at the present time? So in other words, why we cannot choose our present time t0, the finite but sufficiently negative, close to minus infinity, so that your asymptotic expansion showing the instability of Minkowski spacetime may occur just at the present time.
Oh, sorry, can you repeat the second question, please? I'm sorry.
Why we don't see the decay of the Minkowski spacetime at the present time? Or
what does it mean, the decay of Minkowski spacetime?
Why? Well, because it is unstable, as you said. It is once more from the point of your solutions. Why we cannot take your solution and took the present time t0 sufficiently close, though finite of course, but sufficiently close to minus infinity.
Well, interesting question, but actually, I don't understand what is the decay of Minkowski spacetime. I don't think that it is unstable in our model. So sorry, maybe I don't understand the question.
Well,
Once more.
Yulia, I think it's very easy. Sorry, go ahead. Go ahead.
No.
Once more, as I said, your solution for which h becomes growing, it grows at t sufficiently close to minus infinity. Why we don't see this process at the present time? With growing h.
Let me make a comment on this, or answer this question. The Lagrangian depends on the field. In Yulia's talk, it was depending on time explicitly, but when you go to conventional formulation of ADM, then the Lagrangian depends on the field. If your field is sufficiently large and negative, then the flat space is sort of unstable, and that's genesis. Now, as the field rolls, the situation is different, and what we have done was to make sure that as field becomes very large, then field value becomes very large, then the theory reduces to massless scalar field, conventional massless scalar field, and then Minkowski is stable. Okay, we are in kination stage where.
And what is the characteristic time of its growth, of the field?
Well, it's in our hands, but the time scale is can be large. It's not macroscopically large probably, but it can be as large as you want. I mean, the different regimes happen at different values of the field. At large field values positive, you are in more or less standard GR, whereas backwards in time at large negative times, you are very far from conventional GR. And the Minkowski is unstable, you get genesis.
No, well, then the second part of my question is just of the structure of this point. Is it settled point?
We didn't consider. I mean, the perturbations about this solution are not growing, but the solution itself is not static. It develops from constant scale factor to increasing scale factor. So
well, your answer is in some sense that you have some some specific conditions. Of course, you may choose some specific condition in the classic case, but I don't understand how a quantum system may live in infinite time in an unstable state.
Well, it is stable with respect to small perturbations. It's linearly stable, definitely. The solution, the background is linearly stable.
Well, still H becomes to grow somehow.
Yes. It slowly grows in the beginning.
Well, so it's not stable.
What?
I don't understand. I mean, what do you mean by stability or instability?
Well, if the system is in completely stable state, it will remain in this state forever. So this is it's a generic question of first push.
Yes, it's a question of first push. Yes. Yeah, I mean, you see, asymptotically at large negative times, you get Minkowski and infinite minus infinity in the field space. So you go from very large negative fields, and in some sense, yes, indeed, the infinity in field space is sort of unstable. That's right. And there is an issue of the first push.
That's why my generic remark that it's really genesis is not really the very origin. Sometimes something was should be before.
Something stable should be before genesis.
Not stable. Just the opposite. Just some branch, attractor branch, which will bring you to the state. Well, to the state corresponding to a particle just at the upper, at the height of a hill. Well, okay. This is
thank you.
Discussion. So, in some sense, what I want to say, in classical that theory, you may consider the full evolution beginning from a particle just at the height of the at the up of some hill. In classical, in all quantum theories, all of this will have some characteristic time.
Mm-hmm.
So something was before.
Yeah, I think also what Alexei Alexandrovich was asking, one can shape it a bit differently, saying whether your solution is an attractor or not.
This is, I guess this is an additional question.
Yes. It was actually the remark that theoretically it's a kind of saddle point. So it has some curves in phase space which goes to this point, but of course it should have at least one which goes out.
Mm-hmm.
Okay, I think we have further two questions, but very, very quickly. So, Sergey, I think you were the first. Go ahead.
Yeah, your model includes some scalar fields. Can you say something about evolution of those scalar fields?
Okay. Okay. Scalar field about scalar field phi. You mean?
Yes. How it looks like? It has no singularity.
Well, let me remember. If I'm not mistaken, the evolution of scalar field connected with time is exponent of scalar field proportional to time. And if I'm not mistaken, the value of scalar field grows with time. If I'm not mistaken.
So at present time it is very large. Should be very large. This scalar field. But, there is no contradiction between the observation and existence of so large scalar field at present time.
For example, in bounce model, we have. I can show you at the kination epoch for bounce model. We have the solution for scalar field. You say that we can be in contradiction that scalar field have a big value, yes?
Yeah, maybe if it comes to infinity.
Yes, yes, I see.
Okay, guys, there were other questions. Maybe we should go ahead with them. You can continue discussing it per email. I think, Sasha, do you want to ask something very, very quickly? I mean, Sasha Zakharov.
Okay, but it's just one question. So your consideration is very nice from theoretical point of view. And what do you think about perspective to find some typical observational features of signature of your model, just to distinguish your model from other ones?
Yeah, of course, we want to study power spectrum of both scalars and tensors in our models, for example, in Bowles or in Genesis, and we can compare, for example, air tensor to scalar value with observation, or scalar spectral index with observational. Also, we can compare it with observational data. And of course, we really need in relic tensor gravitational waves, but unfortunately, I don't think that we will have it in near future. So, but we can deal with scalar spectrum index and tensor to scalar ratio, and somehow understand is our models of bounce and Genesis are viable or not, in agreement with observational data or not. So this is our current work, current problem to find power spectrum in the bounce and Genesis models.
Okay, thank you.
Okay.